Introduction to Statistics, Chapter 3, Numerically Summarizing Data, Section 3.2, Measures of Dispersion. The range, abbreviated with a capital R, of a variable is the difference between the largest and smallest data value. Finding the range of a set of raw data. We have two options. Option 1, by hand. You can use a calculator and the following formula. Range equals largest data value minus smallest data value. Option 2, you could use StatCrunch. First, you load the data into StatCrunch just like we did in Section 3.1. Select Stat in the top menu, Summarizing Stats, select Columns. Under the Select Columns, choose the column you wish to summarize. Under Statistics, choose Range. And 5, click Compute. Okay, looking at an example on StatCrunch. If I take this, we have a student's names and we have travel time. So if I want the range, I'd click Stat, Summary Stats, Columns. Select my column. Travel time is my column I want. I want to find range. So if I look in statistics, it's not listed in this window. So I have to use the slider bar on the right. Slide down until I see range. Click on range. And you will see range comes over here to the right. Click Compute. And over here to the far right is your answer. So the travel time range is 36. And if you look at the set of data, looks like 45 is the largest, 9 is the smallest, 45 minus 9 is 36. But you can use StatCrunch, especially if you have a large set of data. All right, back to the video. Standard deviation of a set of data is used to describe how spread out the data is from the mean. The deviation about the mean for a single observation is the distance an observation is from the mean. So that's the individual value minus the mean. And that could be a positive or negative number. When finding standard deviation, you must know if your data set is from a sample or a population. The formulas are different. The population standard deviation of a variable is the square root of the sum of the squared deviations about the population mean, divided by the number of observations in the population. So there's the formula. The Greek letter sigma represents population standard deviation. Capital sigma, xi minus mu quantity squared, is the sum of all individual deviations about the mean. And n is the size of the population. Now, you will not or should not be using this formula to find your answers. You should understand that sigma is the symbolism for population standard deviation and use StatCrunch to find your answers. So using StatCrunch, same as before. Load your data, select Stat, Summary Stats, Columns. Select the column you wish to summarize. Under Statistics this time, if it's a population standard deviation, we're going to pick the unadjusted standard deviation and click Compute. So, looking at our example from before, here's our example, travel time. We go up to Stat, Summary Stats, Columns. Pick travel time for our column. Now in Statistics, I see standard deviation, but I don't see unadjusted. So I'm going to go to the slider on the right, scroll down, unadjusted is near the end. So here's unadjusted standard deviation. You would click it, compute. And it's 12.84 if you round off to 2 decimal places. All right, now, sample standard deviation of a variable is the square root of the sum of the squared deviations about the sample mean divided by n minus 1, where n is the sample size. And again, here's the formula. Looks very similar except for different notation. Instead of sigma, you have s for a sample standard deviation. Instead of mu, you have x bar for the mean of a sample. And instead of n, capital N, you have n minus 1 for the sample size. So S represents sample standard deviation. Sigma of xi minus x bar, quantity squared, is the sum of all individual deviations about the mean. And n minus 1 is the size of the sample minus 1. Again, you're not going to use this formula. You should use StatCrunch, but understand that S is the symbolism for sample standard deviation. We call n-1 the degrees of freedom because the first n-1 observations have freedom to be whatever value they wish, but the nth value has no freedom. It must be whatever value forces the sum of the deviations about the mean to equal 0. Using StatCrunch. Again, load, select stats, summary stats, columns, select the column you wish to summarize. Now, under stats, this time you choose the STD DEV, standard deviation. So click compute. Going back to our sample. Okay, you would go up to stat, summarize stats, columns, click travel time for the column. Now, in statistics, here's standard deviation. Just click standard deviation. This is for a sample. Click compute. And now round it off to 2 decimal places, 13.62. Okay, now let's go under options and edit. This time I'm also going to go down and I'm going to pick up the unadjusted standard deviation. So I'm going to have, the first one here is going to be for a sample, this is going to be for a population. If I compute, I now have this. So for a sample, it's 13.62. If it was a population, it's 12.84. So you see the standard deviations are different. Same set of data, but if you count it as a sample, you get one standard deviation. Count as a population, you get a different. So you need to know whether you're dealing with a sample or population. All right, when working with standard deviation, remember the following. Use the symbol S to represent the standard deviation of a sample. Use the symbol sigma to represent the standard deviation of a population. If you are given S, you are working with a sample. If you are given sigma, you are working with a population. Interpretation of the standard deviation. The larger the standard deviation, the more dispersion the distribution has. In other words, a set of data with a larger standard deviation will have a data wider spread from the mean than a set of data with a smaller standard deviation. Let's look at an example. Take data set 1, data set 2. Both data sets have the same mean, mu equals 50. Standard deviation of the first data set is 3.9. Standard deviation of the second data set is 17.7. Now, what does this mean? It means the data in the second data set is more spread out than the data in the first. Let's look at it visually. So if we draw a line for mu equals 50, and now I go up 5, down 5, and make a graph. I'm going to go from 30 to 70. Now I'm going to plot my first point, 45. So there would be 45. Second would be 55. Third would be 52, 2 above, and then 48, 2 below. And this would be my data set 1. Now, draw the same graph for data set 2. This time, the first data is 35, 65, 30, 70. This data set also has a mean of 50, but you notice the data is more spread out because the standard deviation is larger, but it has the same mean. Now, the variance of a variable is the square of the standard deviation. So the population variance is sigma squared. Using StatCrunch to find variance of a population. Again, same steps. Load data into StatCrunch, select stats, summary stats, columns. Select the column you wish to summarize. Now, under the statistics, this time you're going to pick the unadjusted variance. Remember, if it's a population, it's always unadjusted. And click compute. The variance of a variable is the square of the standard deviation again. So the sample variance is S squared. And again, using StatCrunch, you would load the data, select stats, summary stats, columns, Click on the column you wish to summarize, and under statistics, this time you just choose variance. Click compute. Now, if I would go to the sample we did earlier, okay, if I click stats, summary, columns, click travel time. Okay, here is the variance. That's going to be the variance of a sample. If I scroll down, I'll hit unadjusted variance. So if I hold the control key, hit that, I get both of them. Click compute. So if this data set was a sample, the variance would be 185.53, rounded to 2 decimal places. If this was a population, the variance would be 164.91. You notice there is a difference in the two. First, the variance is for a sample. Unadjusted variance is if the data was a population. So you need to know before you find variance whether you have a population or a sample. Now we want to talk about the empirical rule. If a distribution is roughly bell-shaped, then approximately 68% of the data will lie within one standard deviation of the mean. In a population, approximately 68% of the data lie between mu minus 1 sigma and mu plus 1 sigma. That's the mean plus 1 standard deviation, mean minus 1 standard deviation. In a sample, now we're going to use different notation. Still 68% of the data, but it's x bar minus 1s, x bar plus 1s. Again, it's the mean minus 1 standard deviation, mean plus 1 standard. It's just notation. Different for a sample than it is for a population. Also, if a distribution is roughly bell-shaped, then approximately 95% of the data lie within 2 standard deviations of the mean. So in a population, that's going to be mu minus 2 sigma, mu plus 2 sigma. In a sample, it's going to be x bar minus 2s, x bar plus 2s. Finally, if a distribution is roughly bell-shaped, then approximately 99.7% of the data lie within 3 standard deviations of the mean, which means if it's bell-shaped, then basically almost all the data is within 3 standard deviations. There's only 0.3% of the data not within 3 standard deviations. So population, that would be mu minus 3 sigma, mu plus 3 sigma. Sample, x bar minus 3s, x bar plus 3s for the interval. Now let's look at a picture. Here's a picture of a bell-shaped curve. Okay, mu is in the middle, the mean is in the middle, and we're going to do this for population. So mu is in the middle. If I take mu minus 1 standard deviation, go 1 standard deviation to the left, mu plus sigma, that's 1 standard deviation to the right. That's going to be 68% of the data. Since this is bell-shaped, that means that 34% is to the right, 34% to the left. Now, we go out 2 standard deviations. We go 2 to the left, 2 to the right. Now, this is going to be 95% of the data. So now, this was 34. So that means this whole side over here is going to be, what, half of 95? So now this becomes 13.5. So this whole thing is 47.5. So this would be 47.5, which adds up to 95%. Go out 3 standard deviations. We go out 3 standard deviations. Now there's 99.7% of the data within 3 standard deviations. So this was 47.5. I need to add 2.35% to get this and this to add up to 99.7. And on the outside, there's only 0.3%. So that means 0.15% here, 0.15% here. And if you add up all the percents, you would get 100%. Now, how can we use the empirical rule to answer questions? If the exam scores on a recent exam were approximately bell-shaped with a mean of 80 and a standard deviation of 5, well, you draw your bell-shaped curve, okay? The mean would be in the center, so 80 would be in the center. You go 1 standard deviation, 2, 3 standard deviations to the right, 3 standard deviations to the left. So now you have 80, 85, 90, 95 to the right, 80, 75, 70, 65 to the left. First question, what percent of the students scored between 70 and 90 on this test? Well, on a curve, you're going to go from 70 to 90. So that's within 2 standard deviations. So that answer would be your 95%. Question B, what percent of the students scored above 90? Now we have to look at the chart. Where's above 90? Above 90 would be where the yellow is. And if I add those 2%, 2.35 and 0.15%, that's 2.5%. So 2.5% of the students scored above 90. What percent of the students scored below 70? Well, now the yellow shows below 70. And again, you add the percentages, you get 2.5%. Now, the empirical rule only works if you're using numbers that are actual standard deviations. Chebyshev's inequality. For any data set or distribution, at least 1 minus 1 over k squared times 100% of the observations are within k standard deviations of the mean, where k is any number greater than 1. That is, at least 1 minus 1 over k squared times 100% of the data lie between mu minus k times sigma and mu plus k times sigma, for k greater than 1. So, if k equals 2, then we have 1 minus 1 over 2 squared times 100%. Well, 2 squared is 4, so now we have 1 minus 1 over 4 times 100%. 1 minus 1/4 is 3/4 times 100%, which is 75%. Hence, at least 75% of the observations are within 2 standard deviations of the mean. If k equals 3, then it's 1 minus 1 over 3 squared. Well, 3 squared is 9, so 1 minus 1/9 is 8/9 times 100% is 88.9%. Hence, at least 88.9% of the observations are within 3 standard deviations of the mean. You see how this is a little different than the empirical rule, because this distribution does not have to be bell-shaped. Empirical rule, it had to be bell-shaped. And this brings us to the end of section 3.2.